Hi. This is joint work with Abdelraouf Wadjaout and Antoine Minet, my supervisor. This work was originally presented at SAS 21 in COVID mode, and we really thank the organizers of Splash for these COVID time papers in person. Well, not quite in person in this case because I have COVID again. Um, so a word on Indianness first. There is no consensus on the representation of a multi-byte scalar value in computer memory. Little Indian systems store the least significant byte at the lowest address, while big Indian systems do the opposite. Little Indians include Intel processors, while big Indians include Internet protocols and legacy or embedded processors such as Spark or PowerPC. Note that such a conflict might even trigger religious wars, such as the war Gulliver witnessed when traveling to the land of Lilliput. There, he met little Indians who insisted that eggs should be broken at the little end and fought big Indians who wanted to do the opposite. Now, Indianness is an important source of portability errors, especially in the case of low-level C programs. The C standard leaves indeed the precise encoding of scalars partly unspecified. As a consequence, running the same source code on platforms of opposite Indianness can lead to different behaviors. Also, porting software originally developed for one platform to a platform of opposite Indianness can be quite challenging. So let us illustrate this on a simple example. Here we have a very small program originally written for a big Indian platform. It reads a 2-byte input into variable x, then it copies x to y, and then it reads y using the big Indian convention. The value is 1. Now, what happens if we run the same code on a little Indian platform? Well, we get the same bytes, but when reading y with the little Indian convention, we get a different value. Now, if we would like the same value, we have to change the code by replacing the assignment here with a byte swap here. So we read x, byte swap x into y, and when reading y with the little Indian convention, we get the same value as with the big Indian version. Now, if we merge together the two versions of the program using conditional inclusion directives, for instance, we get a so-called Endian Portable program, which ensures that both program versions read the same value for y. Note that there are other ways to byte swap x into y, such as bitwise arithmetics. Now, we call a program Endian Portable if two Endian-specific versions thereof compute equal outputs when run on equal inputs on their respective platforms. In this talk, we present a static analysis by abstraction interpretation that is able to infer the Endian portability of large low-level C programs. So after this motivating example, let us describe the syntax and semantics of the language. So we deal with two versions of the same program, a little Indian version and a big Indian version. So we have so-called double programs, which are joint syntactic structures that we developed in previous work on patch analysis to automate regression verification. Double programs, they have double statements, and double statements are either simple C-like statements or pairs of C statements, pairs of simple statements. The parallel sign here denotes syntactic difference, such as the differences introduced by conditional inclusion directives. Note that even when both program versions share the same code, the semantics might be different, as assignments, for instance, do not write to memory in the same way. Now, simple statements are standard C-like statements where all left values are assumed to have been preprocessed to scalar dereferences. Scalar types include integer types, and pointers. Expressions support pointer arithmetics at the level of bytes and non-deterministic choice. There are also additional statements such as the assert sync statement here, which asserts that both program versions should read the same value for the argument expression. Now, how do we define the semantics of such double programs? Well, we simply lift simple program semantics. Simple C programs are parameterized where they're ABI, in which case we're interested in their Endianness, which is going to be little or big-endian. Their states are simple states, which are standard stores, actually partial functions from addresses to values, where we model addresses as pairs with a base variable and an offset. And then the semantics of simple statements is completely standard. Um, it is an input-output relation over simple states. Now, to move on to double statements, to double programs, uh, we do double states. Double program have double states, which are pairs of simple states. This is the little Endian state, and this is the big Endian state. And the semantics of double statements are relations over these double states. Now, to define the transfer functions, we leverage previous work on patch analysis. Um, for instance, the semantics of composing two syntactically different statements here is simply pairing the semantics of individual statements, such as run in their respective environment with their respective Endianness. We use this construct to define the semantics of assignments. The semantics of the assert sync statement simply checks whether uh, uh, evaluating expression E in each environment gives the same result. Otherwise, an alarm is raised. Now, when moving to compound statements, the semantics is defined by structural induction on the syntax. For instance, the semantics of sequential composition is simply composing the semantic functions. The case of the if statement is a bit more involved. Um, uh, it may have double conditions when the conditions are different. Um, and it distinguishes indeed between four cases instead of two cases, um, using the F filter here for double conditions. Um, the two first cases here are called stable cases. Um, um, in these cases, both program versions agree on the value of the test expression. Here it's true for both, here it's false for both. The stable cases are actually standard, and the two last cases are called unstable cases. Um, for instance, in this case here, we compose the little Endian version of the then branch with the big Endian version of the else branch, filtered by the negation of the filtered by the condition for the little Endian program and the negation of the condition for the little Endian program. Intuitively, this means that the little Endian program runs the then branch and the big Endian program runs the else branch. And that is the dual case. The semantics of loops is defined as a list fixed point. The loop invariant basically says that both program versions run jointly the loop body as long as the, the loop condition is true for both program versions. But as soon as the loop condition turns out to be false for, say, the big-endian version, then this version simply waits, while the little Endian version continues running the little Endian version of the loop body. And both versions meet again after the loop. Now, we have defined the semantics of double programs at a high level, but we yet have to define how um, memory accesses are performed in memory reads and writes. And for that, we need a memory model. At the most concrete level, each program version holds values for individual byte. But we deal with C programs, which have multi-byte access to memory, and we want to compute numerical invariants. Hence the need for scalar cells, which are synthetic scalar variables holding values for the memory dereferences. In addition, we deal with low-level C programs, which tend to abuse unions and pointers to to bypass the weak type system of C and gain byte-level access to the encoding of scalars. As a consequence, cells might overlap. We leverage a previously developed abstract domain by Minet to deal with such low-level C programs. This is the cell abstract domain. Memory is viewed as a dynamic collection of cells holding values for memory dereferences discovered during the analysis. More precisely, a cell is a tuple with a base variable, an offset, a scalar type, the encoding epsilon of the cell, which the cell can be encoded in little endian or big endian, and the native endianness of the platform, which can be the same as the cell or not. And then using this memory model, you can perform a static analysis using any numerical domain. Simply use one dimension per cell. Now let us use the cell domain to do Endian portability analysis on the motivating example. So here on the left, we have the representation of the little endian memory, and on the right, the representation of the big endian memory. When reading equal bytes into the bytes of X, the memory domain synthesizes 1 byte cells for X in both memories and records equalities in the numerical abstraction. Then, the little endian program byte swaps X into Y, which creates 1 byte cells for Y in the little endian memory. Then, the big endian program reads X from the values of overlapping 1 byte cells. It synthesizes this cell, and we have this equality. Then it copies X to Y, so we synthesize YB, and we have this equality. And finally, both program versions read Y, so we synthesize YL from overlapping 1 byte cells, and we query the numerical abstraction for equality. Equality here can indeed be proved from the program invariance and cell constraints that we have inferred. Yet, proving this equality would require an expressive domain such as polyhedra, and this is not an option as we plan to scale to large programs. Fortunately, we noticed that we are mostly trying to infer equalities here, and mostly equalities between multi-byte cells or single byte cells that are matching scalar fields in both memories. And this is not a surprise, as we expect that both program versions will hold equal values for most multi-byte scalar fields during execution with only local deviations. So what we do is we simply optimize the memory model for this common case. And we do this by sharing the representation of cells in the memory environment. We use a single representation for 2 cells coming from different program versions and holding equal values, which we call a B cell. A B cell is either a single cell, only on one side, or a pair of cells on each side, holding equal values, which we call a shared B cell. A shared B cell may represent an equality, or it can represent an equality modulo byte swapping if cells and platforms have different endianness. Let us reanalyze the motivating examples with the B cell domain. Okay, we first merge the representation of memories here, and when reading equal values to the bytes of X, we synthesize immediately shared B cells for the bytes of X. When byte swapping X into Y, we synthesize 1 byte cell for Y and record equalities. When reading X, we synthesize XB, and when assigning X to Y in the big endian memory, we synthesize YB and record equality. And then, when both program versions read Y, the memory domain does not try to synthesize YL. Instead, it first attempts to synthesize a shared B cell for the bytes of Y as a proof of equality. And it does it by looking at a number, by matching the memory abstraction against a number of possible patterns, such as the following. It first looks for a shared B cell that would already exist. Well, it's not the case here. It might also query the numerical domain for equality, but as we said, that would be extremely costly and require an expressive domain, so we don't do it here. Instead, we'd look at further patterns, such as the following. Can we find a cell C in the memory abstraction that would be equal to both YL and YB? Well, XB is a candidate because we have this equality here. So is XB equal to YL? Well, we look at overlapping 1-byte cells for XB and YL. And as they have opposite Endianness encoding, we query exactly for these equalities here. And as a consequence, the test succeeds, and we can synthesize a shared B cell for the bytes of X, for the bytes of Y. And the success of this shared B cell synthesis relies only on this abstract pattern matching and on 3 equalities here, which can be inferred using simple symbolic propagation or a full equality domain. Just to summarize, with simple cells, with not B cells, with cells, we had 2 representations for memory, the 2 representations of the 2 memories, and when reading Y, yes, we also had a lot of pressure on the numerical domain with complex equations, and when reading Y, we synthesize YL and query it for equality. When moving to B cells, we have a single representation for memory, for the 2 memories. We have much less pressure on the numerical abstraction, and when reading Y, we synthesize the shared B cell using mostly abstract pattern matching. Okay, but this is not quite enough. Indeed, most Endian portable programs rely, or at least partly, on bitwise arithmetics to do Endian portable constructs, and not only type punning with pointer casts. So we have to support that. So we have here an idiomatic example where both program versions read the same byte into variable y. The Little Endian program puts this byte at the low order in the 2-byte word x and puts ff at the high order. The big-endian program does the opposite. And we want to infer that both program versions construct indeed the same 2-byte word. Well, this could be done again with expressive invariance and polyhedra, and actually a little more than polyhedra, because the B cell constraints, the relations between 1-byte cells for Y, the 1-byte cells for X in the Little Endian and Big Endian memory are not quite linear expressions. So we don't do that. Instead, we use a symbolic predicate domain inspired by prior work on symbolic constant propagation and predicate domains from Minet. And we basically map every cell with a bit slice expression to which it is equal. It can be top if we have no information, or it can be an expression which is can be a constant or a cell, or a bit slice of a cell, a slice between bit I and bit j, possibly shifted of k bits, or it can be a sum of disjoint bit slices. In practice, in this example, our transfer functions infer that the Little Endian versions of x is equal to this sum of slices here, simply the shared B cell for y and this number. And in the Big Endian memory, we have at the low order 255, and at the high order, we have the shared B cell. So, and additionally, the B cell constraints from the memory domain are interpreted by the numerical abstraction using these B cell, these symbolic expressions here. So when querying for equalities here, we replace the variables with the expressions bound to them, and we have a simple algebra with simple symbolic simplification, which allow to prove equalities and thus synthesize shared B cells for the bytes of X. Okay, we have implemented this work on top of the OPSA platform, which allows for modular development of precise static analyses for multiple languages and multiple properties. Our prototype is a few thousand lines of OCaml, half of which for the B-cell-based memory abstraction, a third of which for automatic double program construction, and the rest for double program iterators and utilities. Our prototype leverages much more lines of the MOPSA platform itself, with parsers, utilities, a large common framework, and iterators and with iterators and numeric domains, either specific for C or generic for all languages. In the implementation, this is a look at the architecture of an analysis of C program with cells. This is not Endian portability for now. This is just C programs with cells, for instance, runtime error analysis. We have a sequence here of iterators for the statements of the language, either C-specific statements or universal statements, such as while loops. And then we have an abstract domain here, which is composed of a memory abstraction at the top and numerical abstraction at the bottom. The memory abstraction is based on cells and handles C machine integers and pointers, while the universal numerical abstraction uses standard domains such as intervals and polyhedra. When moving to Endian portability analysis with B-cell and bit slices, we reuse most of the iterators for C and universal iterators. We add on top of it specific double program iterators, such as the iterator for the if statement, if you recall. And we change the abstract domain. We only replace the cell domain with the B cell domain, and we add a reduction between C machine numbers and bit slices. And as we want to scale, we remove polyhedra. Now we have experimented our work on open source and industrial software. We analyze open source software projects available on GitHub with multiple patches related to Endian portability bugs here. We analyze small slices thereof using our specification primitives. We're able to find all reported Endian portability bugs, and we're also able to prove Endian portability without false alarms where applicable. We'll also analyze two modules of a prototype avionics application developed at Airbus. This avionics application is designed to run on a big-endian platform. Nonetheless, the two modules here, A and S, are designed to be portable to Little Endian, as they are also used as part of a simulator which runs on a Little Endian platform. These are quite large code bases, 1 million lines for A, 300,000 for S. We analyze them quite precisely with 0 false alarms related to Endian portability. And for module A here, all findings have been incorporated into the development cycle because we have been working in cooperation with the avionics development team and the simulation integration team. And as a consequence, the simulation integration team were faced with 0 Endian portability bugs when integrating module A into their simulator for the first time. To conclude, we have developed a static analysis of Endian portability. It is based on a novel, concrete collecting semantics that is able to relate the behaviors of two versions of a program running on platforms with different Endianness. We have a joint memory abstraction able to infer and represent symbolically important relations between the Little Endian and the Big-endian memories. It allows for scalable static analysis. We have a prototype static analyzer that scales to large industrial software with no false alarms. So future work is now ongoing work, and we have started with the industrialization of this work. We plan to use the Endian portability analysis to support avionics certification objectives related to simulation fidelity. And we would also like to extend our approach of portability analysis to further ABI-related portability properties, such as portability across platforms featuring different layouts of C types, which we have already largely done. And what we have not done at all, portability across platforms, featuring machine integers with different sizes. What we have also done is we do not do only portability analysis. We do also regression verification, which aims at proving that two program versions do the same thing on the same platform. And so we do patch analysis, and we in particular do static analysis of patches modifying data types as they change the offsets of fields, for instance. And our B-cell approach is quite effective in this case. So I thank you very much for your attention, and I'll be happy to take your questions.
Okay, thank you. So we have a little bit of an issue with the microphone, but I'll try to relay questions. So are there questions? Looks like nobody's willing to step up. So I can just say it's really an impressive system, and it's really nice to see static analysis in action, that you can actually, it seems to actually matters in practice and make a difference there as far as your results look like, right?
Yes, we're very happy that this works and scales to real software. We, well, we didn't hope that it would work so fast, so we're quite happy indeed, and we hope to be able to use the analysis for for real projects. Well, we have already started actually, and to use it for certification, and that's for the portability analysis. And in this talk, I did not mention a lot patch analysis because this was not the focus of the paper, but we have a related we have other analysis for double programs. Double programs come from patch analysis in the field of regression verification, because actually we see portability analysis as an extension of regression verification. Indeed, portability analysis is about comparing the behaviors of two versions of a program running on different platforms, while regression verification is about comparing the behaviors of two versions of a program running on the same platform. So we use these double programs and this double memory abstraction for both. And we hope to use our patch analysis also in a different context. We have product lines approaches with software components, and so forth. And we would like to automate impact analysis when changing some components using our patch analysis, actually.
So I have one question out of curiosity. So when you demonstrated these double semantics, so you had these cases where the tests came out differently in one side than in the other. Yeah, so those incompatible cases also for loops. Do you have any kind of statistics from your analysis runs? How often things like that actually happen?
So this is extremely rare, and when it happens, we it is rare that we have a precise analysis, actually, because when that happens, sometimes for the analysis to infer that both program versions still do the same, you need a relational domain, right? And we try to scale with mostly non-relational domain by leveraging the double memory abstraction. And so most of the work is indeed to infer that these cases do not occur, to discover that most or nearly all tests are stable. Because as soon as you have an unstable test, you usually have a problem, um, sometimes a precision issue, actually. Um, but it usually fares well because with our B cell abstraction, if we have B cells everywhere, when you do a test that that's based on an expression that only uses variables or fields or pointer dereferences that all resolve to shared B cells, well, they're guaranteed to have the same value, so you have a stable test. So this is the vast majority of tests are stable in our setting.
And if you have a report, an error report, can you also give some sort of counter example? I mean, your analysis is sound, right? So it doesn't have false negatives. But
Right.
in case of a in case of a positive, can you also like give a concrete example of a
Uh,
value where things go wrong?
for now, we have not at all looked into that. Um, so we over approximate. So
There must be false
f-
positives, right?
yes, yeah, there are. It is fine tuned to work on the examples. Well, it's not examples. I mean, on the application targets we have. So we have no false positive for now on the current version of this application. But yes, there are false positives. Obviously, if you take completely general example, a very general code, you're going to have false positives. And we for now we're not able to provide counter examples. No.
Okay.
Uh,
I asked enough.
maybe we would need a backward analysis, a backward double program analysis to be able to come back to the origins of alarms and try to generate counterexamples.
Yeah, thank you. So I asked enough questions so that someone else got inspired to ask the final question. Go ahead.
Hello. Thanks for the talk. So I have a question. Is that if I understood correctly, your double statement semantics it allows to transform a question about an hyper property that you want to compare different execution traces into a straight property. So I was wondering if you have studied some connection with other techniques that does like taint analysis to answer also a question about hyperproperty or relation with the hypercollecting semantics. Um,
Yes, yes, that's a great question. So this was not the main focus of this talk, yet. Um, um, oh, sorry, I have some issues. Yeah, but yes, uh, we our double program setting allows to compare two versions of a program. Okay, so it's a sort of it's a form of self-composition, such as introduced by Barth et al. At some point. Um, and so if it is usually used to analyze two versions of the same program that have different syntax, different source code. But you can also use it to analyze twice the same version of the program. And in this case, um, uh, instead of comparing executions of two programs, you compare sets of the execution of the same program. So you base our double program semantics in this case indeed expresses um, two hyper safety properties, right? Um, and so we have experimented on examples from the related works, such as Barth and others, um, on some simple examples where the authors want to discover some information flow properties, such as secrecy and termination, insensitive non-interference. And it turns out our semantics allows to infer these relations quite efficiently, usually only with non-relational domains. Um, and so there is indeed a link with this line of work that we have not. Well, in some papers we have side notes on that, but we have not developed that much for now. We hope to develop it maybe in the future. Yeah. Oh, yes, and
Okay.
I put this slide because yes, that was an example. On the left, you have well, just look at the left. You have a program that reads inputs. So let's say, both versions of the program read the same input, and then there is a secret that's a random number. So each version of the program has a possibly different random number, which is the secret, and then um, the code well assigns a public variable to one and then resets it to zero, and we output the public variable. Well, this program is secure, and our analysis proves that uh, output here is an assert sync that works, so that both program versions output the same value. Now, if you change the program, you have instead of reinitializing public value to zero, you increment it. Well, our analysis discovered that it cannot prove that both program versions output the same public value. So the analysis simply discovers that the program leaks the value leaks the sign of the public value. So this is just a very simple example where where analysis is able to prove secrecy and fail not to prove secrecy when it's not secret, right? That's it.
So thank you, David. So I guess we have to stop at this point.